next speaker will be Andrea Cherubini, who is a professor at l'IRM, University of Montpellier, which I'm very familiar with his research because we've been working on a European project, Sophia. He's been doing a lot of physical human-robot interaction in terms of vision and control. We look forward to his talk. I can see that his presentation is ready. Andrea, the stage is yours. Please go ahead.
Can you hear me?
Yes, loud and clear.
And you can see the presentation as well?
We can see you and the presentation, yes.
Okay, awesome. Okay, thanks a lot for inviting me. It's a great pleasure to be in this workshop with such a prestigious panel. So I'm not sure I deserve such a stage, but thank you again. It's a virtual stage, so I make it virtual as at best. I entitled this Perception to Interaction. So this is inspired by the perception to action paradigm, which was itself inspired by the principle in neuroscience of reactive control, which was at the basis of visual servoing and force control. And which is also the focus of my research on human-robot interaction. So the research on this, it was inspired by a first European project which we obtained in 2017, which was named Versatile. The project targeted some industrial applications where we wanted to push the physical human-robot interaction into the factory of the future in a flexible process, typically with three main pilot cases, which were from the automotive, aerospace, and consumer good industry. And this led to the design of a cobot, so a collaborative robot in University of Montpellier called Bazaar, which you see here, which is composed of a dual arm system with two shadow hands and a bunch of sensors and an omnidirectional base. Following this, we had a second project, Sophia, mentioned by Arash, who is coordinating it at IIT. The goal here was more focused on ergonomy, so social physical interaction skills, in particular dealing with how to anticipate psychophysical states during work and in the context of heavy tasks in the industry. So the goal of the project, which started less than a year ago, is to design wearable system, wearabots, and collaborative robots, which can help the workers in the factory of the future. So the context of physical human-robot interaction, as you, I think, all know, is on one hand to reduce the ergonomic problems which are encountered by humans in various contexts, both in service and industrial environments, by merging on one hand the skills which are specific of humans, which are adaptability and precision, and on the other hand, the robotic power and speed. So we can distinguish basically two types of tasks, the divisible and interactive ones. You can see in this image on the left a divisible task where the robot and human work separately, but on the same part. And on the right, you see an interactive task where they are working together on the same part. So there can be contact or not, and the contact can be desirable or not. In the case of physical collaboration, on the other hand, the contact is really desired and it is aimed at achieving a common goal. So we have some challenges. In my opinion, the most important ones are safety. So for this, there has been a lot of work, well, much of it coming from Sami's group about specification and standards for safe robots. There has to be human intention recognition, so you have to detect and also track over time what the human intends to do. And finally, you want the robot to be versatile and flexible and to deal with different, very varied range of objects and of situations. So I will address these three challenges separately in my presentation, starting by safety. So I hope you can see here somehow. But mainly this is work we did a few years ago. So we presented this dummy industrial scenario where we wanted the robot to help a human in a drilling task. So the driller is activated by interacting with the tactile sensors of the robot. The main contribution here was to present a framework which could deal with the ISO standard on safety, which was ISO 10218, and which required some bounds on velocity, force, and power. So to do this, we used an adaptive admittance controller. So admittance control, as you well known, was conceived by Neville Hogan and also mentioned by Sami earlier. So we'll have the pleasure to hear Neville later today. And we adapted the controller by using a tunable alpha parameter, which could fulfill either the bounds on velocity, on force, and on power. So at each time, the robot was capable of fulfilling the ISO standard. Nowadays, I would use certainly constrained optimization to do this, but at the time we went more via this. Of course, again, on an instance control, but rather than having this self-tunable parameter, we would use optimization. And we were using touch for intuitive programming. Following this work, we developed the software library. So this was mainly the work of Benjamin Navarro, who you see here, which was called OpenPHRI, which enabled easily deployable physical human-robot interaction application. So you can find this library on GitHub. And it's, of course, open access and open source. In this example that you see here, we're dealing with a highly redundant robot. The robot can move and can also move its base, but also its arm. So according to the task, according to where Benjamin puts his, it's the end effector, either the top or the bottom of the system are actuated. And this is one of the many features of the library. The other ones are mentioned in the top right and are also focused on the ISO standard. For the second challenge, human intention recognition. So here we did a lot of work on vision. So in this video that you see here, we trained the robot to recognize American Sign Language signs, which are shown to the robot, and this enables the system to be easily reprogrammable on the fly by the operator. So each sign corresponds to some action that the robot should execute. And to do this, we use OpenPose, which you may know is a very interesting software library developed at Carnegie Mellon for detecting human skeletons on images. And the OpenPose skeleton tracker is used to first detect the hand of the user. And this hand, which you see in the top left of the image, is used to train another convolutional neural network on sign language, enabling the system to recognize on the fly the signs at 5 Hertz. And this was integrated in the OpenPHRI software library, enabling smarter physical human-robot interaction, which doesn't require direct touch with the human. Other work has been done in the context of the PhD of Sony Tarbouyesh, which you see in this video. So Sony was working on extending the admittance control framework to dual arm. So here he developed the generic representation of bimanual task framework, but for cooperative operations. So we're extending admittance control to the bimanual framework, and to detect so he was using inverse kinematics based on hierarchical QP, and he can control a very sophisticated robot, including a mobile base, by using prioritization of the joint at the joint level. One interesting feature of also his system is that he can detect the contact using the OpenPose library, which I mentioned priorly. And using the contact detection, it is easier to infer the intention of the user. These are some examples where the humans are using a virtual reality, augmented reality system to validate their task, which is a collaborative carrying task. I will now go to the last part of the presentation, which is about versatile and flexible manipulation. So we did some work on haptics, in particular how to, this is more, it's still on physical human-robot interaction, but I would say also related to the environment. Some things can be applied also to humans, but in particular on how to make the robot interact with objects and the environment as a human would. So the first work on this was zero-shot haptic recognition. So you may be familiar with the multi-class classification problem, which consists in classifying objects, and it has been very much popularized by the vision community recently with the advent of deep neural networks. And so the classifier is trained on some objects here, bottle, and apple, and orange, and finally it can online detect a bottle. In daily life, there are so many objects that it is really hard to foresee a classifier of this type. So what we proposed was a zero-shot learning system, which can classify an object it has never seen before, like football in this example. To do so, it has to have a knowledge of what a football is like. So it has a dictionary of information about what a football is like. And to carry out this, we used an attribute dictionary where each object was associated to some attributes, and we could learn the attributes by touching the objects. So these are objects the system is trained with. It can learn all the characteristics, and if it meets an object, if it is confronted to an object which is it has never seen before, but it is aware of the attributes, for example, here the robot knows what is plastic and what is a cylinder, it can infer that it is grabbing a tube. And the system is also capable of working with different grasping areas. So this work was extended more recently by integrating also vision. So you can use vision and tact together to learn how to classify objects which have never been seen or touched before by the robot. Currently, we are doing a lot of work on shape servoing of objects. This is also intended to be, in this sense, probably more a divisible task in the context of physical human-robot interaction, where the robot can help a human in placing a cable, for instance, in the factory. So this first work by Jiong Zhu was exploiting the contacts in the environment to do the shaping. So we use visual control and planning strategy here, as well as a formalism developed by Jiong itself called the contact mobility index. And with this, in this context, it's possible to design the motion control such that the cable can be set along the contacts, as you can see in the video. So this work is positioned in a more general framework of research that I'm carrying out on shape servoing of deformable objects, mainly using vision, but we're also looking at touch, and which can be also extended to physical human-robot interaction in the context, for example, of medical robotics, if you look at needle insertion and also surgery on persons. So here we're looking at the contact mobility index to use this, and it's a planning and vision-based framework that was applied to realize this challenging task. Future work consists in developing a generic framework which could address both rigid and soft objects. So here you can look at some results where this time the shape of the cable can be obtained by manipulating the object. These are very recent work by Jeong. And here, this is a sponge, so it's elastoplastic object which can be shaped, and using the same, exactly the same controller without changing anything, we can also servo rigid objects. So the idea behind this work is to use a PCA to extract a subspace of features. In this last example, the object is rigid at the beginning and flexible when it touches the environment, so it can be modeled in both cases, and the system is successful. And here we show a failure case. So I was saying we use a PCA to extract the features, and we are also estimating online both the dynamic, these features from the PCA, and also the dynamics which relate the control input with the evolution of the features, what is called interaction matrix in traditional visual surveying. In the same context, I also worked on more on other types of objects which are elastoplastic, such as this type of sun. This was during my sabbatical at QUT in Brisbane, Australia, 2 years ago. So here the goal is to find the actions which can modify the environment online by using vision alone. So first we acquired a series of images of humans realizing similar tasks, and these images were processed to find the states and actions which were relevant for the task. And then using some various techniques, we could map the state evolution with the action which was required in order to deform the soft material. So it's a model-free approach, which we are currently looking at applying to a model-based method using finite elements. And the work was published in ICRA this year. So after this system has been capable of inferring the relationship between the states and the actions, it is capable of realizing the desired operation with a very good accuracy, which is shown here by the green and yellow dots, the yellow being the ground truth and the green being the output of the network. And we could finally deploy it on the robot. So here we see the robot, which has to realize the image shown in the top left. And to do so, it concatenates a series of actions depending on the contours it sees. And another also currently explored research work in this context is to use robotic hand to extend the actions which are possible. So the ultimate idea is to really be capable of doing complex hand operations to manipulate this type of materials. This is a bit what we mentioned about exploitation of the human data set, comparing different strategies, and the convergence of the mutual information proved that our system was efficient. So to rewrap, we had safety, human intention recognition, and versatile and flexible manipulation, which are the main challenges of our work. And this is just to conclude. I would like to thank all my collaborators and, of course, the robot for making all this possible. And this is a list of the publications which are related to the works you just saw. Thank you very much.
Okay, thank you, Andrea, for a very interesting talk. We have time for one or two quick questions. One question came from Samit, who asks, who comments on the scenarios, which are nice, and he asked, what is the time to react in these scenarios? And I think it is actually referring to the collaborative tasks.
You mean the ones with the gestures?
I'm not sure. Maybe, Samit, can you please elaborate more? Probably on the collaborative task, co-carrying gestures, maybe yes in general, unless we're waiting for his detailed question, but yeah.
Well, in
Yeah,
general,
okay,
our goal in all these works is to, of course, to work in real time, because we want to have the collaboration to be relevant for the human. So this was a big challenge in the gesture recognition work, which of course had to be transferred to real time. There is an issue when roboticists want to use, well, it was historically when roboticists wanted to use image processing and computer vision systems, and it is now the case with deep learning. It's that these communities generally provide excellent results, but they are rarely in real time. And of course, we have a real time specification. So we are always confronted to this when we try to transfer vision methods to robots. And it was the case here. So the open pose is about 5 hertz, 5 to 10 hertz, depending on the machine that is used. If you just track one skeleton, so for multiple skeletons, we have to check. And detecting the hands had to be also implemented in an optimal way to make it run at 5 hertz, but we were capable of doing it. But of course, this is a major issue, in particular with vision, algorithms. For force, of course, I would say we have also some delays, which I'm sure with the results that Sami Hadadin showed before are not necessary, because we have a very high frequency sensor feedback from a force sensor, but we apply some filtering because we don't have the observers which Sami showed about collision detection. But to some extent, I would say for these tasks, since there is some collaboration and it's not a collision, we can take that delay. But for vision, it's more challenging.
Okay, thanks for the answer.